You're watching InTechnology, a video cast where you can get smarter about cybersecurity, sustainability, and technology. Here are your hosts, Tom Garrison and Camille Morhart.
Our guest today is Jorge Myszne. He is co-founder and CEO of Camille, a hardware security startup company. He is a serial entrepreneur with more than 20 years of experience in the semiconductor, communications, and security industries. Jorge has a rare mix of technical and business acumen, having held technical and management roles in big and small companies. Welcome to the podcast, Jorge.
Thanks for having me.
So our topic today, we wanted to talk about root of trust. We're going to start with root of trust. We're going to kind of migrate from there. But Jorge, for all those folks out there that have probably heard the term, but maybe don't fully understand what it is, can we just start with what is your definition of root of trust?
Sure. So basically, we need something that we know to be authentic, that we can trust. And the same way that if we are friends and you present me your friend, so then I will trust him because I trust you and you trust him. So by transitive, I will trust him. So in any computing system, at the end of the day, we want to verify that everything is authentic and everything that we load, specifically the firmware or the software that we load, is authentic. We need to start somewhere. We need to have something in the system that is the anchor of trust that we know to be real. And from there, we can have a friend of a friend of a friend of a friend and just verify that everything, or attest that everything is authentic.
And so if we carry that same sort of analogy or understanding then into firmware and software, root of trust sounds great. I think everybody would want to have it. It kind of makes sense. But why is it so important when it comes to firmware and software?
In the security history, the first threats were at the application layer, right? So people will try to install something that is malicious and that way do things. And as defenses were built and were good enough to stop those kinds of attacks, attackers started to go deeper and go one level down and go into the operating system. Now, the lower you get, definitely more protected, but at the same time is more difficult to find it, to detect it. And you have access to other things. If you are able to attack successfully an application, but it will be difficult from there to go and steal things in other places of the computer. If you are at the operating system, so you see everything that is in that computer, so you are able to do other things. When you go into the firmware, the challenge is that the firmware is loaded before the operating system exists. So all the tools, all the security tools that we use, let's call, for example, an antivirus, it's loaded after the operating system. It's an application or kind of an application. It happened after the firmware is loaded. So if the firmware is malicious, it's very difficult for an application to understand that that firmware is malicious. So that's why we need the root of trust. We need to stop that when it's happening. And when it's happening, there is no software. So it has to be done in hardware. We need to have a device in the system that is the root of trust, that is in charge of verifying that that is correct, that is authentic.
I gave a talk a couple of years ago, and I used the same type of analogy. If you think about the context like a building, where you want to build a building, a secure building, well, the hardware and the firmware are the bedrock. There's nothing below the hardware and the firmware. And so attackers are now basically trying to attack the firmware, because if they can get there, of course, they can defeat all the other defenses that exist above it. But also, there's nowhere else for them to go. There's nothing below the firmware.
The base of the pyramid, if you want. If you get there, it's very difficult to, one, to detect it, but two, it doesn't disappear, it's persistent. You turn off your computer, you turn it on, and it will load the same malicious firmware again. If you are at the application layer, you turn off your computer, and when you turn it on, it's clean. In the case of the firmware, it's persistent. And then you need to go and change it. And if you are a smart attacker, you will disable the update so you can't change it. So then physically you need to go and remove the flash or do something physically. So it's very expensive. It's not just having an antivirus and, okay, let's update the antivirus database. It doesn't work that way. And if you have it in a server, in a data center with 100,000 servers, and you need to find that server and physically open it up and do something, that is very, very expensive. So that's why the root of trust is needed.
How do you recognize this kind of an attack then?
The firmware is loaded in a small device that is called a flash memory, and it's loaded into the processor. And in case of a server, there is also firmware for the BMC, that is a management processor. The root of trust interposes those lines, meaning that when the data is loaded from the memory into the processors, it goes through the root of trust, and the root of trust is checking that code. Now, the root of trust has a manifest, kind of a database, so he knows what should be there. So it just compares. There is signatures, there is encryption, and that's the way that we can verify if things are authentic or not. At the same time, the root of trust also protects the whole update process, because having the first boot being correct doesn't mean that I cannot change it later, and then it will happen later. So there's a lot of protections. For example, if you know that there is a firmware version that is problematic or has a vulnerability, so you can put it in a blacklist, so you don't allow it to have. So if you try to update the firmware to a version that is problematic, so you won't allow to do that, right? If you want to update the firmware, so there is a whole protocol where you need to prove that you have the right authority to be able to do that. And that way, you can guarantee that when the system boots, the code that is there is authentic. Doesn't mean that it's bug-free. It just means that that's what you wanted to have in the system.
Based on your experience, how is it that the attackers actually get to write to the firmware? And do they attack the device itself, or do they go try to mimic themselves as a legitimate firmware update? Or how is it, based on your experience, that this happens?
There are multiple ways that this can happen. First one is in the supply chain. So the system comes from the factory, and somewhere in the supply chain, whether it's in the manufacturer, is during the shipping, someone changed something. Can be a component, can be just the code. And when you get it, the code that you have is not the right one. Mm-hmm. Right? That's one vector of attack. Usually the other vector is remotely, especially for a data center, for a server farm. Nobody wants to physically go server by server and update the server. So there is a way through the system to update that. So usually using some kind of vulnerability in the system, you are able to update the firmware to whatever you want. Now, in some cases, you don't even need to update the firmware. As I was mentioning before, there might be that there is a bug in the firmware, and there is a vulnerability, and you are able to exploit that vulnerability. So the root of the problem is not really the firmware, but that firmware that is a buggy firmware allows you to exploit the system and being able to remotely attack that system. Now, there is a third vector, in my experience, is definitely in a data center setup, is almost non-existent, that is physically going and doing something. Today's cloud setups and data centers have also physical security, so that anybody can go into a server farm. So that types of attacks are rare, but the more we concentrate servers and information, and the information that you have there becomes valuable, that can happen.
So if you were able to launch a firmware attack, I don't know, let's say somebody's PC, but then the PC connects to a server farm, like we were just discussing. Can this attack then at the firmware level tunnel in through the PC down to the server farm, and then once it's there, go underneath the virtual machine monitor and like proliferate throughout a server farm?
Firmware attack at the end of the day means changing the firmware or even exploiting a firmware bug. It's not necessarily a firmware attack. I'm not changing anything on the firmware. I just know that that specific version has a problem, so I can do something. At the end of the day, the firmware is loaded into the memory of the system and runs while the system is running. So if I know that there is a vulnerability that I can exploit, then I can do something. Now, assuming that I'm able to change the firmware, now depends on what I do. What I will do is add some type of vulnerability that then I will be able to exploit during runtime while the system is running. That will allow me to, for example, get access to the network. And if I get access to the network, I will be able to jump from one server to another. And then I might be able to do the same on the next one. So it's very specific of what I do with that and how I am able to insert the vulnerability and exploit it later.
How do companies protect themselves against these attacks? Based on your experience, I mean, obviously you're working at a company right now that specializes in helping companies start with the basics and then work your way up to the more sophisticated ways of protecting yourself.
Actually, the protection starts in the supply chain. And there are things that we do while the root of trust is added into a motherboard, a server motherboard, to bind it to the memory. So be able to detect if someone changes things. So we try to connect everything in a way that we can detect any changes that happen even before the system is turned on. And then when the system is turned on is what I explained before. We have a manifest, we have a database, we know what it should be there, and we need to verify that what we have is there. And eventually we also can interrogate peripherals that are on the system and verify that those peripherals that boot by themselves are also original and authentic.
It seems like just the basics of making sure that your device, whether it's a server or a client or any device, just has the latest firmware. That's one important step, because as you pointed out, these attacks are sometimes just leveraging buggy firmware, and as a result, you may be exposed to some issue that you didn't realize. But if you just move to the latest update, you'd be protected.
How prevalent are these attacks? Because it sounds a bit more difficult to launch one of these than, say, from an application layer.
Definitely, it's more difficult, and you need, I would say, a more skilled hacker to do it. In the last probably 3-4 years, the amount of firmware attacks have increased by 5-fold. There is an article from Microsoft, I think it's from last year, that they are showing that 80% of the enterprises have acknowledged that they have had firmware attacks in the last 2 years. So it's definitely less common than application attacks, but it's growing exponentially. And the infrastructure today is not capable of stopping them. And that's the main challenge here.
So another question I have is, we've seen critical infrastructure attacks in the news. And I'm wondering, is there a way to protect, I guess we could call them legacy or brownfield systems, or systems that are already in the field, like, for example, a lot of critical infrastructure for these kinds of attacks? Or is it something that you really have to do as you're rolling out the machines?
So definitely it's something that can be done. It's not easy because you need to engineer the solution for that specific infrastructure. Some of that critical infrastructure is very old, right? So it's not just as simple as adding a card or something like that. Most of the solutions today are tailored for the next generation, but definitely there are things that can be done. It will be a tailor-made solution based on the same principles, but it has to be custom-made.
Feels like we could go on this topic for quite a while, but Jorge, I think this is probably a good place to stop. But before we let you go, we do have a segment on our podcast that we like to do, which is called Fun Facts. And so I wonder if you have a fun fact that you'd like to share with our audience.
Sure. Probably when I crossed my 40, I started to think about flying. So I became a private pilot. And today I really enjoy flying over San Francisco. I'm now completing my instrument rating so I can fly into the clouds.
Have you flown to some pretty cool locations?
One of the pretty things to do is just go around on top of Alcatraz. So actually, I've never been physically to Alcatraz, but I know everything from the top.
Yeah, that's great. That's great. How about you, Camille?
Well, I am going to do kind of a simple one today because I am at the coast and getting ready to plant over the next week. So this is some Swiss chard. And I planted some like a couple years ago and it grew like crazy for 2 years with no tending at all. So I thought I would read something about it. And turns out Swiss chard does not come from Switzerland. It originated in the Mediterranean, they think, and it's closely related to the beet, but delicious little veggie that if you're willing to separate the stalk, you know, in this case, it's rainbow chard. So they're all different color stalks. If you're willing to separate that from the leaf when you eat it, if you saute the stalk in saffron and butter, and then separately you prepare the green leaf in like olive oil, lemon juice, and black pepper, it's an amazing combination.
Yeah, this is a cooking show today. This is fantastic. Well, great. Well, I am going completely different, continuing on the theme of sort of the earth we live on and kind of cool little fun facts around that. So we all have heard the fun fact that just over 96% of the total amount of the world's water is held in the ocean. So to find the bulk of fresh water, you actually need to trek to the poles, to the North and South Pole. 68.7% of all the fresh water on the globe is actually encased in ice caps and permanent snow and glaciers. And I was thinking more like the Great Lakes and that kind of thing. But anyway, I was wrong. And I learned something. I thought that was pretty interesting. Anyway, all right. Well, Jorge, thank you so much for joining us. It was a great conversation. Certainly one that we've worked around the edges on over the last couple of years when we've been doing this podcast. We've talked about sort of root of trust, but we've never really dove into it and why it was important. So appreciate you spending the time with us and educating us and our listeners on firmware, root of trust.
Thank you for having me. It was a pleasure.
Never miss an episode of InTechnology by following us here on YouTube or wherever you get your audio podcasts.
The views and opinions expressed are those of the guests and author and do not necessarily reflect the official policy or position of Intel Corporation.